Welcome everybody to our final session of this Quantum Days event of the QWorld, and we are very happy to have this very rich and mixed session where we will talk about sensing and metrology and also complex systems and using quantum technology for research. So our first speaker of this session will be Valeria Sequino, and she is going to present us her work about on helping with quantum technologies to detect gravitational waves, something that is exciting for a big public outside. So whenever I speak about quantum, black holes are always coming as a question. So this is a fantastic talk that combines both. And Valeria is working in Italy, and she is doing an experimental device that is helping this research. So Valeria, please, the stage is yours.
Hi all. In this talk, I will introduce how we use squeezed vacuum states for quantum noise reduction in gravitational wave detectors. Since I'm not able to, okay. Since I know that most of you come from different fields, I want to briefly introduce gravitational waves and gravitational wave detectors. Gravitational waves are transverse perturbation of the space-time produced by non-spherical symmetric accelerating masses, such as binary compact objects, for example, binary of black holes, binaries of neutron stars, or composed by neutron stars and black holes. But not only this kind of sources, but also supernova, pulsars, stochastic background. Gravitational waves were predicted by Albert Einstein in 1916, and they were detected about 100 years later. The first signal of gravitational wave was detected in September of 2005, and 2 years later, the Nobel Prize for this discovery was assigned. Up to now, about 90 gravitational wave signals has been detected. But how we spent so much time to detect gravitational waves? The effect of the gravitational wave is very tiny. If we consider two masses at a distance of some kilometers, the distance between these two change of only 10 to minus 18 meters. This means that is 8 orders of magnitude less than the radius of the atom. And the first attempt to detect gravitational wave experimentally was done by Weber using a resonant mass. But this system revealed to not be too much sensitive, and then the gravitational wave collaboration passed to another kind of device that is more sensitive to such a small distance variance of the distance, and in particular it was chosen to use optical interferometers. Here we can see a simple Michelson interferometer where we have a laser, we have a semi-transparent mirror that is called the beam splitter, and we have the part of the light that is reflected and go to a mirror, the other one that is transmitted, and after the two mirrors reflect back the light, and they arrive to a detector. In this last picture, we can see the effect of a gravitational wave on a Michelson interferometer. The masses that are considered for the distance in order to measure, let's say, the difference in distance of these two are the masses of the mirrors, and the effect of a gravitational wave that impinge in a orthogonal way to the plane where the interferometer is located is to make shorter the distance between two mirrors, and longer the distance between the mirrors that are in the orthogonal direction. But gravitational wave interferometers are much more complex. Here we can see a conceptual design of the interferometer, where we can see that there are some Fabry-Perot cavities in each arm. There are other cavities, for example, a power recycling cavity that is a cavity that is used to collect and to use also the light that go back to the interferometer. And there is another cavity that is called the signal recycling cavity that is used to modulate the shape of the sensitivity curve of the detector. Of course, there are not only these optics, but there are a lot of auxiliary optics, auxiliary benches, also suspended benches that are used in order to have a good shape of the beam, to have to control this all these cavities. The arms of these interferometers are very long. Here we can see an aerial view of Virgo that is located in Italy. This is the experiment for which I work, and Virgo has arms 3 kilometers long. The two other main interferometers are the two that are located in US, the two LIGO detectors that has an arms of 4 kilometers long, and there is one in Hanford and another in Livingston. The gravitational wave detectors form a network where now the operative interferometers are these three, but there are also other interferometers. There is GEO 600 in Germany that has shorter arms. Then it doesn't have the right sensitivity to join the scientific runs, but it is very, very important because it's the interferometer where all the techniques that are used in the other interferometers are tested. And there is another interferometer whose construction house is finished, that is Kagra in Japan. This is an underground interferometer. And now it has not the sensitivity that is comparable with the sensitivity of the other three main interferometers, but it is now progressing. There is also the project approved to do another interferometer in India, and the construction of this will start in the next years. The gravitational wave signal is covered by several noises that disturb the measurement in gravitational wave interferometers. I will list only the main. For example, in the low part of the detection bandwidth that goes to 10 Hertz to 10 kilohertz, is the seismic noise. There is also the coating Brownian noise, that is a Brownian noise that concerns the coating of the mirrors used for the interferometer, and there is a quantum noise that is this violet curve. As we can see here, this is the sensitivity, theoretical, is the simulated sensitivity curve of Advanced Virgo, of the interferometer that participated to the last scientific runs and then detected gravitational waves. We can see that at the high frequency, the sensitivity curve, that is this black curve, is limited by quantum noise, and in particular this quantum noise is short noise, and this is due to the vacuum phase fluctuations. While there is another component of the quantum noise, that is the radiation pressure noise, that for Advanced Virgo was not disturbing, being covered by other noises, but as we will see in the next, this will be also important for the new generation of gravitational wave detectors as Advanced Virgo, that now is in phase of commissioning. The quantum noise comes comes from vacuum fluctuations. Is here a bit of theory. We have the Hamiltonian of the harmonic, the mechanical harmonic oscillator, and the quantization of this harmonic oscillator. We can see that if we consider the lower level of the eigenstates of this Hamiltonian, we have a 0-point energy. There is an analogy with the light wave, with the light wave, and with the Hamiltonian for the electromagnetic oscillator, and the same, we can quantize the electromagnetic field, and we can see that also the 0-point energy for the electromagnetic field is not zero, and there are these fluctuations that disturb the measurement of gravitational wave. In particular, we have that this vacuum noise coupled with the gravitational signal, and the measurement is disturbed. The idea is to circumvent this problem, sending squeezed vacuum states instead that the vacuum, the coherent vacuum that naturally enter the interferometer, as Caves demonstrate in 1981. This can reduce the quantum noise, in particular the shot noise in gravitational wave detectors. Squeezed states of light are particular states of light that are characterized by a reduced noise in one of the two quadrature. We can write the amplitude quadrature and the phase quadrature, and we can write the electric field as a combination of these two. The variances of these two quadrature respect the Heisenberg uncertainty principle. And in particular, we can define the minimum uncertainty states. The coherent states are states for which the error on the amplitude quadrature and the phase quadrature are the same, as we can see also here in where we see that the uncertainty in phase and in amplitude is the same, and this is well represented in the phase space, where we see that this is represented by a circle. Concerning squeezed states, one of the two quadratures is compressed. Then the variance of one of these two quadratures is compressed. For example, for amplitude squeezed states, we have less noise in amplitude and more noise with respect to the coherent case in phase, while for the phase squeezed states, we have the contrary, less noise for the phase and more noise for the amplitude. There are several ways to produce squeezed states, but the solution that we use is to produce squeezed states using an optical parametric oscillator. In particular, we have a cavity with a nonlinear crystal inside. We have a pump beam and the vacuum, and the result is that we have the vacuum that is squeezed. This kind of experiment are old. In fact, the first time it was realized in 1985. And but in radio frequency band, why I underline this? Because for gravitational wave detector, as we saw looking at the sensitivity curve, the detection bandwidth for gravitational wave detector is the audio frequency band from 10 Hz to 10 kilohertz. Then this means that we have to stabilize the squeezing states, and if we want the phase squeezing states to reduce the shot noise, we need to stabilize the so-called squeezing angle. I will show later how this is done, and this was done for the first time in 2007 from the quantum optics group of the Albert Einstein Institute in Hanover, and they also provide us the source to be used in Advanced Virgo. In particular, I will not go too much in details, but I will just show some components of this squeeze-like source. And the general characteristics are that this is built on a board of 1 meter by 1 meter. There are 2 lasers, one at the wavelength of 1064 nanometer, that is the wavelength at which the present gravitational wave detector work. The first laser has a power on 1 watt, and the other laser, that is an auxiliary laser, a power of 500 milliwatts. There are 2 optical phase locked loop, a second harmonic generator cavity. There is inside a Mach Zehnder interferometer. The optical parametric oscillator, this is the source of squeezing, is a doubly resonant one, and there is an Homodyne detector. Here are some details. Here there is the second harmonic generator cavity that is similar to the optical parametric oscillator. Here the effect is that we send this light, the infrared light, and we will obtain a green light that will be used as a pump for our OPO. The power of this pump is stabilized using a small Mach Zehnder interferometer, whose length is controlled with the control system. The OPO cavity is a cavity that is a semi-monolithic cavity. It is composed by a nonlinear crystal of PP kappa TP, and one of the mirror is the curved face of the crystal. The crystal is very small. It is of about 1 centimeter of length, and the section is of 1 millimeter per 1.5 millimeter. And there is also an external mirror that has a piezo here that control the length of the cavity. The control is done using the standard technique of pound river roll, and this makes the cavity resonant for both the green light and the infrared light. In order to detect the level of squeeze, measure the level of squeezing produced, it is used an Homodyne detector that is essentially composed by a beam splitter and 2 identical high quantum efficiency photodiodes whose photocurrents are subtracted. If we don't have the squeeze vacuum, we can measure the quantum noise, the shot noise of a laser. We have this beam that is called the local oscillator. That is a beam that is much brighter with respect to the squeeze beam. This is mode cleaned using a triangular cavity, then in order to make it a perfect Gaussian mode. And when it arrives to the 2 photodiodes, all the classical noise are subtracted, and only the shock noise is measured. When we also put the squeeze vacuum on the beam splitter, we have that the level of the shot noise decrease, and this is the demonstration that the squeeze vacuum states can reduce the quantum noise. This is the 2 lasers. The 2 lasers are optical phase locked loop, in sense that there is a system that allows these 2 beams to have always the same difference in frequency, and the frequency is chosen in order to have a beam that also experience the nonlinearity of the OPO, and this is used to implement the technique introduced by the Albert Einstein Institute to fix the squeezing angle. In particular, since this is the squeezing angle that allow the squeezing states that determine the state of the squeezing, in sense that if it is squeezed in phase or in amplitude or in a combination of these two quadratures. And it depends mostly on the phase of the pump beam that go inside the OPO. With this system, it is possible to fix the phase of the OPO. We have the second harmonic generator beam. We have here an actuator that is a piezoelectric actuator to which it is sent an error signal in order to fix the phase of the pump. But when once we fix the phase of the pump, we have also to fix the phase of the local oscillator that in our measurement is our reference system. In fact, a similar control system is applied to a mirror along the path of the local oscillator. In this way, we are able to produce the squeezing in audio frequency band that are used for gravitational wave detectors. Once what I described is just the source of squeezing, and we have an internal Homodyne detector, and then what we measure is the reduction of quantum noise of an auxiliary beam that is this local oscillator. But what we want to do is to reduce the shock noise of the beam of the interferometer. Then this picture is not in scale. This is our 1 meter per 1 meter squeezing light source, and this is our interferometer with the arms of 3 kilometers long. This is to show the interface. First of all, the two lasers, the laser of the interferometer and the main laser of the squeezer should be optical phase locked loop, and we have for example here we have a Faraday isolator that is an isolation stage to protect the squeezing cavity from back reflected light, which introduces excess noise in audio frequency detection band. We have a mode matching telescope that is constituted by two of axis spherical mirror for residual astigmatism compensation, and the mirrors are mounted on micrometer stages for beam waist size and position fine tuning. There is a triplet of Faraday isolators. Each of them has 1% of losses. They contribute to a 40 dB of isolation, the suppression of the backscattering from the light leaking from the interferometer. Moreover, there is an auto-alignment system that is composed by two mirrors that has a separation of 1 meter, and they are used for initial tuning, and they provide the actuation for automatic alignment of the squeezing light into the interferometer. Finally, there is another Faraday isolator that is used for the injection, and we know that all the mirrors of the interferometer are suspended, and they are in vacuum tanks. The squeeze beam entered the vacuum system through a wedged optical window, and this allowed the injection into the interferometer through the output booster polarizer of the Faraday isolator. This system brought good result. This is the sensitivity curve of of Advanced Virgo, the one that participated to the last scientific run and then to the detection of many gravitational wave candidates. And here we can see the sensitivity curve in absence of squeezed light, with the squeezing light, and then we can see an improvement of the sensitivity of 3.2 dB. And here in blue we can see the measurement of the anti-squeezing. This means that we change the squeezing angle in order to have anti-squeezing and then squeezing in amplitude. This measurement is not what we need. We need the other one, but this is used to measure the losses, because this measurement is related to the losses into the interferometer. This corresponds to have 5%, 80% overall sensitivity improvement of the detector, and a binary neutron stars detection rate increase of 16% to from 16% to 26%. This is what I showed. I showed is what happened for advanced Virgo, and but now the interferometer is in phase of upgrade. Actually we finished the upgrade, and now we are in phase of commissioning, and many changes were done, and mostly to improve the sensitivity of the interferometer in the low frequency part of the detection band. And since the quantum noise is a noise that we cannot eliminate, this now is the noise that also limit the sensitivity of the interferometer in this part of the detection band. But as I said some slides ago, the radiation pressure noise that is in this that is the component of quantum noise in this part of the detection band is related to the amplitude to the amplitude of the vacuum fluctuations. This means that since we still have the shot noise, this means that we have to rotate the squeezing angle. We need a phase squeeze state in the high part of in the high frequency bandwidth, and we need an amplitude squeeze states for the reduction of quantum noise in the low frequency part. In order to do this, the technique that we use is to use a filter cavity, an external filter cavity. We produce the squeezing, the frequency independent squeezing, and we send this squeezing in a detuned cavity. This detuned cavity can rotate the squeezing angle, and this is what we want for our interferometer. This technique has been already tested in past. The first demonstration for the working of this technique was done in the megahertz region in 2005 using a cavity half a meter long. And 10 years later, there was the first demonstration of the working this technique in the kilohertz region using a cavity 2 meter long. Only in 2020, there was the first demonstration of the rotation of the squeezing angle using a filter cavity for frequencies below 100 Hertz. We're using a cavity 300 meter long. This was done in the Now-J group in Japan. And this is the first time that the technique was demonstrated for frequencies of interest for gravitational wave detectors. The need for 100 meter long cavity is because this has less squeezing degradation induced by the cavity losses. And if we want references to explain this, we can see here. And now we also did some some preliminary measurement in Advanced Virgo Plus, and we were able to achieve very good results, even if they are preliminary. I will not show these results because they are not yet published. Now I will show the modification that we did to the interferometer in order to add a new cavity that is about 300 meters long. In particular, we know that in the tube of Virgo, in this blue tube, there is another tube where we have the light of the interferometer, and parallel to this, we built another vacuum pipe here, another tube, where there is the light and there is the filter that goes towards the filter cavity. In order to do this, we had to do also infrastructure works. In fact, we had to raise the roof. These are because we have the mirrors that are of the filter cavity that are also suspended to some pendulums. And here then we have in this part of the roof, here we have the first mirror of the filter cavity, a 300 meter long, after we have the second mirror of the cavity. The characteristic of this cavity is to have the mirrors are that the mirror have a diameter of 15 centimeters, lower than the one used for the interferometer that are 35 centimeters. The radius of curvature is around 500 meters, and they have the cavity has a round trip loss less than 40 parts per million. Advanced Virgo Plus required a squinting angle rotation of about 25 Hertz, and this justified the need for a cavity length of the same order, and then the choice of the length of the cavity of the finesse that is 11,000 at the frequency of interest. The cavity, as I said before, to work and to have the squeezing angle rotation must be detuned with respect to the frequency of the squeeze beam, and then the locking of the cavity will be done using another infrared laser that we will call subcarrier, and subcarrier, and we have also the locking with the green. That is a pre-locking of the cavity with the beam that has a finesse that is lower, because to lock a cavity with such a high finesse is more difficult. This is a conceptual design of the frequency-dependent squeezing system in Advanced Virgo Plus. In particular, we have an external bench that is in air. We have two suspended benches and some auxiliary benches. Of course, we have our filter cavity. In this bench, that is the inner bench, we have this subcarrier external laser. This laser, as I said before, is used to lock the filter cavity, and the cavity then will be resonant for the frequency of this beam, and this should be slightly offset with respect to the main squeezing laser in order to make the squeezing beam slightly detuned with respect to the cavity. This laser will go first inside the OPO and will be completely reflected by it, and this will help to be the beam co-propagating with the squeezing beam, and this beam will be used for, as I said before, for the longitudinal, but also for the angular control of the filter cavity, and also as a probe from mode matching between the squeezing beam, the filter cavity, and the interferometer, because we are not to forget that our squeezing beam is the vacuum squeezing. Then we need a bright beam that is co-propagating with our squeeze beam and can help us in aligning and mode match. The filter cavity has the characteristics that I said before, and already said this, and it is, I will show after the infrastructure, and then you will see how it is located with respect to the bench. This is just a scheme. There are also mode matching telescopes, in particular 3. This is the first mode matching telescope that is composed by 2 curved mirrors. We did not use lenses because this we have to try to have as less losses as possible. And we have a first mode matching telescope to match the squeezing beam with the first suspended bench. We have another mode matching telescope that is composed by 2 curved mirrors, each placed on different suspended benches. In fact, this I will show how we did this this system. And finally, on this suspended bench, we have the telescope to send to adapt the beam to the beam of the interferometer. There is here this double stage Faraday isolator that is important, because with this is a Faraday double Faraday isolator. Then between the 2 Faraday isolators, we have an half-wave plate. With this half-wave plate, we can change the polarization of the light coming back from the filter cavity, and we can decide if we want to have a diagnostic measurement and then to send the light, the squeeze light, towards the external Homodyne detector that is placed on the external squeezing bench, or if we want to send the beam to the interferometer. This the first case is useful to measure independently from the interferometer how much squeezing and the rotation of the squeezing angle. This is the infrastructure, and then here maybe one can have an idea of how the system is done. Here we have our external bench where we have the lasers, the squeezing source, and so on. The first suspended bench is here. Here we can see the vacuum tank, because this is the bench is suspended and is under vacuum. There is here this pipe that is 12 meters long. This is the second squeezing suspended bench. And as I showed before, here we have a mirror for a telescope, and here we have the second mirror. Then we have to balance very well the benches and in order to have straight beams. And here we have a pipe that here is not in scale, but this is 80 meters long, and this is our filter cavity, 300 meters long. Here are some pictures. We can see the vacuum tanks, the one for the second, the first and the second suspended bench, the one for the filter cavity, where we have the input mirror, we have here we have the cavity, we have the pipes that I showed in the picture. This is an overview of the benches. We have our squeezing source. This is our breadboard of 1 meter per 1 meter. We have the external inner bench, that is this one. Here some particular thing on the bench. There is a viewport that connects this inner bench with the suspended bench. Here we can see the suspended benches outside the vacuum tank, here inside the vacuum tank, but with the vacuum broke, because we have to break the vacuum to, of course, to open the tank. this bench is fluctuate, and we have to control it with a sophisticated control system. This is the double stage Faraday isolator. This is the second auxiliary bench that also is suspended and in vacuum. These are auxiliary benches. These are in air and are not suspended. Now to conclude, what I showed is how we use squeezed vacuum states to solve the problem of the quantum noise in gravitational wave detectors. I showed that this was successful for Advanced Virgo, showing a reduction of shot noise, and concerning the frequency dependent squeezing in Advanced Virgo Plus, I can say that I said that the installation is completed, that preliminary measurement showed that the system works, and now all the system is in phase of commissioning and it will be ready by the end of this year, when the fourth scientific run will start. Thank you all for your attention.
Many thanks, Valeria, for this very, very good introducing talk about the challenges in measuring gravitational waves. I'm super happy. Today we have already heard about squeezed states that were used in secure communication, and now we have the squeezed states as the saviors again for detecting gravitational waves. And let's see what are the questions of today. So I'm scrolling through the chat, and first of all, we have an admiration, and it is impressive. The Marilou says that it's impressive, all the components that the interferometer has by itself. This is great. And there is a question. This is from me, actually, and I'm curious. On the picture where you showed the curve of the quantum noise, there was a minima for, I think, about 200 hertz. There was a minima in the quantum noise. I wonder, why is it? So what is the actual reason for this minima?
Yes, I will show. Sorry, no, maybe it's here. In sense that you want to know why there is this here, because in general the shot noise is a white noise. Then one has to expect to have a shot noise do in this way. So we have to a flat shot noise, and while the radiation pressure noise has this behavior, it goes as one on the frequency, is inversion proportional to the frequency. But this effect is due to the Fabry-Perot cavities inside the arms of the interferometer that act as a filter. Is because the cavity has a pole in this frequency. That's why we have this modulation of the curve of the quantum noise.
Okay, very good. Thanks a lot. So this is practically the measurement problem. It's not the noise itself, but the measurement of the white noise, practically, because it's a field. Great, thanks. So the next question we have now from Akash, and he is asking, could you please comment why Michelson interferometer is used in detection for gravitational waves, and if some other, probably better interferometer is proposed as a substitute?
Yes, okay. Actually, I don't know why at that time there were not proposed other kind of interferometers, but of course also other kind can work. Maybe also for the construction. It's also a problem of logistic problem. Maybe it was at the time it was decided, but I will ask about this, but I think that this can be the possible answer, that it was easier to build an interferometer with this shape, mostly because it was at the time was very difficult to ask, for example, also to the person that has these countries to build something in the interferometer. Here we have private houses, we have countries, we have cars that has to pass and so on. Maybe this configuration was better. And even there is maybe also another thing that for the effect of the gravitational wave is so we can see looking at the effect that the gravitational wave that impinge the interferometer in the orthogonal plane in the orthogonally with respect to the plane of the interferometer. Here maybe it's easier to see this displacement, and also to have because the idea was from the beginning to have a network of interferometers that are oriented in a different way, in a way that if the gravitational wave pass, we can some of the interferometer can see the gravitational wave. For example, one of the first signal that was detected by Virgo actually was not appearing very well in the sensitivity of it was not appearing very well in the data taken by Virgo, and this was very, very important because this gave some information on the direction of the gravitational wave coming from the space, and the fact that it was seen in a certain way by the LIGO interferometers and less for Virgo meant that as I said already said that very useful information on the sky location of the source.
Great, many thanks. And there is one more question coming. Marie-Luz is asking, at what distance does the curvature of the Earth affects the stability of the mirrors?
Sorry, can you repeat at which distance?
At what distance does the curvature of the Earth affects the stability of the mirrors?
Yes, some kilometers is already enough, in the sense that we already see with the 3 kilometers, we already see the curvature of the Earth. In fact, the tubes are built in a particular way in order to make straight the beam. What will be done, for example, for the next generation of interferometer, where we think to build interferometer of 10 with arms 10 kilometers long, is to build the interferometer underground, not only for this, but also, of course, to limit the seismic noise, but in this way we will be able to have interferometers with the longer arms.
Very nice. Thanks a lot, Valeria. I think there is one more question. We still have 2 minutes. This is fantastic. And this is again a question from me. And I was wondering if there is a plan, or it's anyhow useful actually, to move all these experiments that you have on the table, that is a very big spatially wise experiment, into a chip. I don't know if that is anywhere along the lines.
Yes, concerning the splitting source, there are experiments there are experiments that can are working on not in our collaboration, but are working for to have a very small compact squeezing source. I know that already some years ago there were some encouraging result for the production of squeezing at the frequency of megahertz. Of course, and we, the Italian collaboration, also proposed to have something similar, but this is something that should be tested to have the compact squeezing source also for the new generation of interferometer, for example, the Einstein telescope that should be whose project has been approved, but we have to, it's not yet built. But for that, we can try to see if it is possible to, first of all, we have to do a tabletop, a very small experiment. We have to produce the squeezing in audio frequency band. That is the challenge.
Okay, I see. Many thanks, Valeria, and congratulations with pushing the frequency of detection of this special objects, quasars, from 16 to 26%. This is an awesome result, and good luck for the future. And I would like to invite you to close your screen sharing and to greet everybody and thank the visitors in your native language. We have got this interesting tradition today. If you would
my
like
native language.
Exactly.
Ciao a tutti, grazie per aver seguito questa presentazione. Io sono Valeria dall'Italia, la mia lingua è l'italiano adesso. Okay.
Mille grazie mille,
Ciao.
Valeria.